Hey, so today I wanted to show off Ghost Hunting, which is my approach to detecting the abuse of system calls by malware. So this would be detecting techniques commonly referred to as Hell's Gate and Halo's Gate for the abuse of direct and indirect syscalls. So malware tends to do this to circumnavigate hooks that EDRs put into NTDLL and a couple of other places, where the malware will basically make a direct system call into the kernel so the EDR doesn't get a chance to hook it and inspect it in the DLL itself. Now, I'm writing Sanctum, which is a EDR, bit of a hobby, an endpoint detection and response product. It's all in Rust, it's all on GitHub as well, so I'll throw a link to that in the description below. And the problem that I'm trying to solve essentially at the moment is this abuse of syscalls. So I've got a proof of concept to show, which kind of shows how ghost hunting works, but at a high level, we have two main components to ghost hunting. So the first is from the Sanctum DLL itself. So as every other EDR does, Sanctum injects itself via a DLL into processes running on the host machine. Now this DLL will hook and intercept syscalls that the program's trying to make to have a look at the arguments that are passed into the syscall, try and determine if it's bad, that sort of stuff. Unfortunately, nowadays, this isn't really a strong option just in isolation, because through things like Hell's Gate, Halo's Gate, etc., malware is able to completely bypass this through the use of direct syscalls or indirect syscalls. EDR vendors, of course, have ways and means of trying to detect these things, looking at the stack, etc. I'm sure lots of other fancy and creative ways to solve it. Ghost hunting is my approach to solving this. So to do this, we have to use alt syscalls, which is alternate syscalls. This was first researched by, I forget the name of the researchers, but it was a couple of years ago for Windows 10. Windows 11 changed the interface for alt syscalls, which I've kind of reverse engineered and managed to get working. You can find that on my blog if you're interested. And what this allows us to do in the kernel is intercept syscalls at the driver level, so within the kernel itself. We become part of the system service dispatch process, which is kind of cool. So what we can do is we can fully rely on that to inspect what's going on at runtime dynamically, with no way really of interference other than perhaps through an adversary's rootkit. The original way that I was looking at doing this was through the events tracing for Windows system. So this is something Microsoft expose, where processes through system calls or whatever is going on, Windows can, or those programs can basically emit some telemetry which other things can receive and subscribe to. One of those is the Events Tracing for Windows Threat Intelligence provider, which is only available to early launch anti-malware services, so EDR vendors, antivirus vendors, and that contains information about things typically that malware does that's bad. So one example would be process injection. The interface for those, I struggled to find much documentation on them at all. Whilst I got it working, it wasn't perfect. So it was serviceable if I really sort of put time into, but with the advent of alt syscalls, well, it made sense to use that instead of ETW. So who knows, hopefully maybe alt syscalls can be used by real sort of EDR vendors in the future. It'd be really cool if Microsoft made that a kind of public API, maybe for those ELAM, early launch anti-malware services drivers. That'd be kind of cool. So if we have a look very quickly at the way this works, so we have the two components that we've discussed. The first is via the kernel, the second is via userland. So we'll maybe start with userland because it's a little easier to envisage. The EDR that's in the DLL's process hooks the syscall stub of interest. When a system call gets made, so let's take open process as an example, the EDR will send, the DLL will send a message to the user mode engine, which is an executable that's running via inter-process communication. The engine then sends a ioctl down to the driver. After that happens, the driver receives it in the Ghost Hunt module, which we'll talk about shortly. So I think we'll pause that there and have a look up at the kernel side. So when the system call does reach the dispatcher, alt syscall runs. So first of all, is the syscall one monitored by the EDR? If not, we allow the syscall to complete. We're not really interested in gaining intelligence from that. If it is something that's monitored by the EDR, I've got that in twice. Then we want to package it up for the syscall post-processing thread and send it to that thread. And that will then also add it to the ghost hunt timers in the process monitor. And from the process monitor, we're able to detect whether Hell's Gate or Halo's Gate has been used. Essentially, the way we do that is there's a timer that runs in the processes, in the ghost hunting processes, where we have kind of an upper limit. And if we don't receive both signals within a specified time frame, then we can detect that one of these two things hasn't worked. Either it's a bug or it's malware using direct indirect syscalls. So very quickly then, to show what we're going to do, we're going to run this process injection function in this malware. So this is going to be called malware.exe. And what this is going to do is it's going to open a process. So we're going to specify a PID, a process ID, and it's going to open that process. Now the open process function that we use, I've written to use direct syscalls as opposed to doing it through the kernel 32, kernel base, then ntdll, where the EDR would ordinarily hook. So this malware is doing direct syscalls. So when we call open process, we set up a couple of things that we need to do, and then we call this nt open process function down here. Now nt open process is what we call a naked function that uses naked assembly, which allows us to directly use assembly directly, but it preserves the ABI. So if we were to have arguments here, sort of 5 and beyond, those go onto the stack in Windows as per the ABI, and this just allows us to maintain that kind of integrity without having to then start moving things into the correct positions on the stack. We do then have to call the return instruction, and we can take that handle and return it back to the main piece of the malware. So after we get that handle from open process, we just do a simple DLL injection. So we have the path to a DLL, we allocate memory for the string as to where that DLL resides, we write the path into the remote process, and we then call create remote thread, pointing the address of load library into the thread start and the allocation address where the string resides in that process, so that it can open that DLL or it can inject that DLL. Fairly standard. So what we'll see is ghost hunting in action. So there's two components to the EDR. We've got the user mode side and we've got the driver side. This is the GUI, the front end to the engine. So if we start the EDR, we can see here just some prints that we get. So we have Notepad open, which is going to be our sacrificial process, and let's grab its PID 11216. We also have malware.exe here, and this is evil DLL which we inject. You could see that in the source code. So let's run malware.exe and we pass in the PID. What we'll do is I'll clear the debug view, which allows us to see those kernel prints from the driver, and we will run the executable. Now the first thing we get is the DLL, the Sanctum DLL itself pops up a message just saying that it's injecting into a process that spawned. We'll click OK, we'll let it run, and we can see that it attempted to open the process. It then made a memory allocation. It wrote 43 bytes. You get the handle of, or the address of kernel32.dll, the address of load library, and we start a thread, and this is the thread ID that we get back, or the handle, the thread handle. So let's go and look at the debug view. In fact, let's have a look. We can see here that we have injected the DLL. This is the message in Notepad. Nice. So looking at the prints, we can see, first of all, that it's detected a sensitive API in the start address of the thread, which is load library A. This is going to come more relevant in a future update where it fully detects DLL injection, but we'll park that there for now. The next thing is just some debug prints around the fact that it's adding the ghost hunt event to the ghost hunt process monitor. So we can see that first of all we've got nt allocate virtual memory, nt write virtual memory, nt create thread x, nt open process. Now we should get those twice if we didn't use direct syscalls. So one is a source from the DLL, one is a source from the alt syscalls handler in the driver. In this case though, for nt open process, we have exceeded the ghost hunting timer for that syscall. So we can therefore infer that direct syscalls was used. This is evidence of malware. We might want to stop the process once this is detected, etc. So that's kind of it really. What's next for the EDR? As I've kind of said, working towards detecting and blocking remote process injection. So this is both for DLL injection and shellcode injection, and I also want to extend that to APCQ hijacking to detect and or block that. I'm also working towards memory allocation tracking, so this is on both the process doing the injection or doing the allocation and the process that receives the allocation. So one thing that I'm kind of conscious of is, let's say you have kind of 3 helper pieces of malware, one of which injects some memory, one of which changes the write protections on that memory, and the other one writes to the memory. Technically, that's 3 different processes operating on the same victim, and that may bypass EDR. So by tracking both the kind of offending party and the victim party, we're able to say that the target process is having bad things done to it, and we're able to also attribute those to the remote processes, and that would be a great kind of threat hunting opportunity for a detection analyst. So I'm working towards those things. Hopefully I'll post an update in that in the future. So thanks for watching. I hope you found that helpful. If you do have any questions, please feel free to reach out to me. This stuff is very much a passion project, and I would love your feedback and opinion. Thank you.